Having previously had a look at Kirchhoff's current law, we'll here be moving on to his second circuit law, his voltage law. And then we'll look at a brief example where we use the pair of them together to analyse a circuit and see the sorts of things that we can determine from doing so. In doing so, we will also be touching on Ohm's law to determine some of those values. So Kirchhoff's voltage law states that in a closed loop, the sum of the EMFs is equal to the sum of the PDs. So the sum or the total voltage we're putting into the circuit is the same as the total voltage we're taking out. And to illustrate this, I'm just going to use a small counter example to help me out. So let's say we've got a cell and it's connected up to a pair of resistors. And the cell has an EMF of, let's go for 6 volts. And these two resistors, regardless of the value, let's say we've measured that the potential difference hit across here is 4 volts and the potential difference across here is 3 volts. So let's follow a coulomb of charge coming from here, and being E minus, it's going to go against the flow of conventional current, so it's going to come around in this sort of direction. Actually let's have it start over here. So we start over here with no energy. We pass through here and we pick up 6 volts per coulomb of charge. So 6 joules of energy, 6 volts, so 6 joules of energy per coulomb of charge. So at this point we have 6 joules per coulomb. We carry on round through the wire, we ignore the resistance there, we get to this point, so we've still got 6 joules per coulomb, or 6 volts. We pass through this resistor and 3 joules per coulomb is taken out of the circuit. So at this point here we're down to 3 joules per coulomb. We hit the other resistor, we pass through and we lose another 4, which gives us minus 1 joule per coulomb, and that takes us back around here to minus 1 joules per coulomb, having started at 0 joules per coulomb. So if this is so, then every time this amount of charge, this coulomb of charge, completes a single cycle of the circuit, it's going to lose 1 joule. So we start with no energy. After one circuit we've lost a joule, another circuit we've lost a total of 2 joules, another circuit we've lost a total of 3 joules. Similarly, if this was only 2 volts, then here we would have plus 1 joules per coulomb, and similarly back here plus 1 joule per coulomb. And so each time we complete one cycle of the circuit, we're gaining 1 joule per coulomb of charge. Now this unfortunately violates the conservation of energy, so we know that energy cannot be created nor destroyed, and so if in this setup, in the setup with the red text, we are destroying 1 joule of energy every time we go around. If we've got the blue one, we're creating 1 joule of energy from somewhere every time we go around. And obviously neither of these are very agreeable with the conservation of energy, so neither of these can be true. And so what we will see instead is that either this one's got to be 3 volts and the other one 3 volts, or if this is going to stay as 4 volts, then this would have to be 2 volts, and that means that when we complete the circuit we're back to 0 joules. So when we complete this loop we must have that the sum of the EMFs is equal to the sum of the potential differences. So if we go, so the sum of the EMF must equal the sum of the potential differences. So this 6 volts is equal to the 3 plus either the 3 plus 3 or the 4 plus 2. Exactly how the voltage divides would depend on the exact value of the resistances of these two resistors, and that can actually be determined quite readily, but we'll cover that another time. So sum of the EMF in is sum of the energy out. And remembering that these are in voltages, that's energy per charge, so for a given charge, energy in equals energy out, just the conservation of energy. So just as Kirchhoff's current law was actually nothing more than a manifestation of the conservation of charge, Kirchhoff's voltage law is actually nothing more than a manifestation of the conservation of energy. So now we can have a look at a quick example. So here we've got a circuit. We've got again a 6-volt cell connected up to two resistors in parallel, one 1 kilo ohm resistor and one 470 ohm resistor. And we've got 5 quantities labelled on here. So the voltage across these 2 resistors plus these 3 currents. So the current passing through this resistor, the current passing through the lower resistor, and the total current passing through the cell. So these 2 voltages are going to be the easiest ones to work out first, and we do that using Kirchhoff's voltage law. So if we imagine starting from here and following this current around this loop of the circuit, we can see that there is only one EMF and only one PD. And knowing that the total EMF, this 6 volts, must equal the total potential difference, V1, means that the voltage dropped, the potential difference across the 1 kilo ohm resistor, must be 6 volts. We can then form another loop. So we can again come around here, but this time come along the lower resistor. And again we have only one EMF and only one potential difference, so the voltage across V2 is going to be 6 volts. So Kirchhoff's voltage law allows us to draw a little simplification to make things a bit easier when we're looking at parallel circuits, and say that in parallel circuits the voltage across each branch is equal. So that's V1 and V2. Just as a brief aside, if we were to have a look at the loop which goes around here, so through this resistor and then back along here, then we would say along this loop we've got no EMF but just 2 potential differences. So how can Kirchhoff's voltage law apply across this point? And the answer to that is that along here, if we're going in this direction, we're going backwards through the resistor, whereas through here we're going forward. So if this amount of charge when passing here is going to lose energy, if we're going backwards, then that's kind of equivalent of gaining energy. So because if we go backwards through a resistor, then that would actually count as an EMF. If we go backwards through a cell, then that would count as losing energy. So around here it still applies because we're going backwards through this resistor, and so that counts as a negative 6 volts against the plus 6 volts here, which gives us 0. So it still applies, we just have to be careful about the direction we're applying it in. Next up, let's have a look at I1. So we know the voltage across here, we know the resistance of it, and so we can use Ohm's law. V equals IR, gives us I is equal to V over R, so we get 6 volts divided by 1 kilo ohm, which gives us 6 milliamps. Across I2, exactly the same thing, but in this case we've got 470 ohms instead of the 1 kilo ohm, and so that gives us a value of 12.8 milliamps. For I3, we're going to go back to Kirchhoff's current law. So that says that at this loop the total current entering it must be the same as the total current leaving it, and so we say I3 is I1 plus I2, so that is equal to 6 milliamps plus 12.8 milliamps, which gives us 18.8 milliamps. So we can see here that we've now got a very powerful set of tools in these 3 laws that we've come across. So Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law combined together allows us to quite readily do some in-depth analysis of circuits.